Welcome to the next session on virtual labs. In this session, we are taking up the third experiment of machine dynamics and mechanical vibration lab. The title of the experiment is Free Vibration of Fixed Beam. We'll first check out the aim. The purpose of the experiment is to determine the logarithmic decrement, damping ratio, damping frequency, and natural frequency of a fixed beam under free vibration. We'll go to the theory part. There are few learning objectives. After completing the simulation experiment on free vibration of a fixed beam, one should be able to model a given real system to an equivalent simplified model of a fixed beam with suitable assumptions or idealizations. Here, both the ends of the beam are going to be fixed, hence it is called as fixed beam or fixed beam. Calculate the logarithmic decrement, that is delta, damping ratio zeta, damping frequency omega d, and natural frequency omega n of the system. Find the stiffness, that is K, and the critical damping of the system, that is Cc. Calculate damping coefficient of the system, that is C. So these are the various variables that we are going to find. It is similar to the free vibration of cantilever and simply supported beam. If you have gone through those two experiments, this will be an easier one for you. Introduction. A system is said to be a fixed beam system if it has a fixed connections at both its ends. Vibration analysis of a fixed beam system is important as it can explain and help us analyze a number of real-life problems. The following few real systems can be simplified to a fixed beam, thereby helping us make design changes accordingly for the most efficient systems. Following few figures tell us about the significance of analyzing fixed beams and their relevance to the real world. So here you can see example of a real system is a suspension system. Both these ends are going to have this kind of a pillow lock joint. Now they are supposed to be fixed here. So it is easier to analyze this kind of a beam when these two ends are fixed, and you can accordingly design for the system such that it has a critical damping. You can determine the stiffness of this suspension material based on what choice of material you make. The above figure depicts a fixed suspension system and the pillow lock joint at its ends. In machinery too, we can find parts which can be analyzed as fixed beams, like in grinding machines and furnaces. So these two machines can also be brought down to fixed beams and you can accordingly analyze them. Natural frequency of fixed beam. When given an excitation and left to vibrate on its own, the frequency at which a fixed beam will oscillate is its natural frequency. This condition is called free vibration. The value of natural frequency depends only on system parameters of mass and stiffness. In this case, there is no damping considered. When a real system is approximated to a fixed beam, some assumptions are made for modeling and analysis. The first one is the mass m of the whole system is considered to be lumped at the middle of the beam. No energy consuming element damping is present in the system, that is, the system is undamped. The complex cross-section and type of material of the real system has been simplified to equate to a fixed beam. So we are going to assume few cross-sections like I section, L section, a square cross-section or a circular cross-section. The governing equation for such a system is given as below. Mx double dot plus kx is 0. If I divide throughout by mass, I'll have x double dot plus omega n square x is 0. K is the stiffness of the system, is a property which depends on the length L, moment of inertia I, and Young's modulus E of the material of the beam. And for a fixed beam, it is given by 192 EI upon LQ. Next, we will talk about damping being introduced in this fixed beam. Although there is no visible damper or dashpot, The real system has some amount of damping present in it. When a system with damping undergoes free vibration, the damping property must also be considered for the modeling and analysis. Single degree of freedom spring mass damper system under free vibration is governed by the following differential equation: mx double dot plus cx dot plus kx is 0. Cx dot term has been added now. When you divide throughout by mass, you will get x double dot plus 2 zeta omega n x dot plus omega n square x is 0. C is the damping present in the system. Zeta is the damping factor or damping ratio of the system, which is nothing but the ratio of damping C and critical damping Cc. Critical damping can be seen as the damping just sufficient to avoid oscillations. At critical condition, zeta is 1. For real systems, the value of zeta is less than 1. For a system where zeta is less than 1, the differential equation solution is a pair of complex conjugates, and this is the displacement equation where x0 and v0 are the initial displacement and velocity of the system. And for calculating omega d, this equation has been given: omega n root of 1 minus zeta square. Now suppose if I know the value of omega d and I know the value of zeta, or I am able to set the value of zeta, I can calculate what is the natural frequency of the fixed beam. So this is the procedure given. The procedure is exactly the same as that of the free vibration for cantilever and simply supported beam. So you can refer that video for the explanation of procedure. I'm not repeating it again. For this experiment, a self-evaluation tab has been given. So you can just check out this and test your knowledge. We will directly go for the simulation. Here I am choosing the material as steel. You can just slide over steel and you can see the value of E is given as 200 gigapascal. You can choose any cross section. Let me choose the cross section as circular. You can see the diameter is given as 150 mm and the value of I is given as 2485.05 centimeter raised to 4. So when I convert this in terms of mm, this will be 2485.05 into 10 raised to 4 mm raised to 4. Let me choose the length as 1000 itself, the way it is given. Let's take the damping ratio value this time as 0.8. The central mass is 25 kg. Let me make it to 73.5 kg. Now let's start the analysis. And this is the graph. You can see immediately it has come to a halt. It's because of the central mass being quite heavy. So let's make this a bit lighter. Just refresh the page. As you can run it only once, and let me make this to 30 kg. So the values have been set. This is the graph and these are the values given to us. You can cross check these values by using these formulas. So we can just start with zeta. We have taken the value of zeta as 0.8 and accordingly I can calculate delta by substituting in this formula. I get this value as 8.3775. Next we will go for calculating K. It is 192 EI upon L cube. Just make sure that this time the material is steel. So the value of E is 200 gigapascal. So substitute accordingly. I'm getting the value as 954,259.2. Next we can calculate omega n by using this formula. Omega d value is given here. I get the answer as 3435.1816. Unit is radians per second. Next, we will calculate M equivalent. I get the answer as 80.866 kg. Don't forget to convert this into Newton per meter. That's correct. Then we can calculate Cc using this formula. I get the value as 555579.42. Unit is Newton second per meter. And for calculating C, I just multiply this answer with 0.8. So I get the value as 444463.54. You can check the value here. It's close and correct. Apart from this, you have the tab for assignment given. 2 questions are given here. You can just try these 2 questions. And this is a quiz given. You can try that. A video shows how to use the simulation tab. There are a few references given. And finally, a feedback tab is given where you can give your feedback. So with this, I end the session. I hope you have understood how to analyze the free vibration of a fixed beam using virtual lab. If you have any doubt, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.